welcome to this video on kinetics of rigid body. So let's consider this question. It says, in figure 1, bar AB rotates with an angular velocity of 10 radians per second clockwise. What is the linear velocity VR of the rack and pinion gear? Okay, so we are basically asked to find the velocity of this rack. This is actually a rack, so you can indicate here as arrow, and we are asked to find velocity of the rack. Now this is the whole system, and we are told that AB is rotating with an angular speed of 10 radians per second clockwise, so which means it's going about this direction. And in all the videos I've done on kinetics of rigid body, I've said if an arm is rotating with a given angular speed, then at the free end, remember we have 2 points, the fixed and the free end. So point A is fixed, then at the free end we are going to have a velocity which is at 90 degrees to the surface, and we call that VB. And we simply said that velocity is going to be what? The sum of the velocity at the fixed point plus the radial arm, which is radius between A to B, multiplied by the angular speed between A to B. But let's observe these dimensions first. We were given 12 inch, 6 inch, 16 inch, and 10 inch. So we need to convert all of these first to meters. Now to do so, 1 inch, okay, 1 inch is equivalent to 0.0254 in meters. So it means that to convert 12 inch is going to be what? 12 times 0.0254 in meters. So 12 inch will give us approximately 0.3048 in meters. So I'm going to be employing all of this to convert all the given dimensions. So you can do that just to save time. You can do that yourself as well. So these are the converted values of all the dimensions given to us. Okay, another thing you should keep in mind, please mind you, in this question I am going to be employing the vectors approach to solving this problem. So unlike all the videos we've done so far under this particular topic, okay, in this particular video we are going to be using the vectors approach so you can know how to solve using the two of them. Anyone that is convenient for you, either the vectors or the ones I've talked about previously, you can use. Now, in using the vectors approach, you keep this in mind. Okay, you know that this is always going to be our J direction, which is the y-axis, will be our J direction. The x-axis always is going to be our I direction, and then of course this is our, which is the z-axis is going to be the K direction. Now, in rigid body motion, always keep in mind that it is only the angular speed that moves in the K direction. Okay, every other dimensions moves either in the I or in the J axis. So mind you once more, if you're moving towards the positive X direction, you have positive I. If you're moving towards the positive Y direction, you have positive J. But if you're moving against the X direction, that means you're moving backwards. Now let's say you want to locate a point and you're moving backwards, it becomes negative I. If you're moving downward vertically, it becomes negative J. Keeping that also in mind. Another thing you need to keep in mind when using the vectors approach is the cross product of vectors. Okay, so let's just do a brief summary of our cross product. So in summary, when we have I cross J, the value is simply what? K. When we have J cross K, the value is I. When we have K cross I, the value is J. Similarly, when we have K cross J, the value is negative I. When we have J cross I, the value is negative K. When we have I cross K, the value is simply negative J. So keeping all of this in mind, I've also said that only the angular speed moves in the K direction. And from the question, we are given that if the angular speed, we are given that arm AB rotates with an angular velocity of 10 radians per second. So this simply means that the angular speed of arm AB, omega AB, is equal to 10 in the K direction, because it is only the angular speed that moves in the K direction. Alright, so in the videos I did earlier on this particular topic, I explained that whenever you're solving any question involving kinetics of rigid body, you always do well to start analyzing from the fixed point. So we have two fixed points here, point A and point D is fixed. So always start your analysis considering the fixed point. So we can start with point A since point A is fixed, and okay, and I also said to find the speed at point B, which is the free end now, we are going to have the equation to be. So the velocity at point B is given as velocity at the fixed point, which is point A, plus the position vector between A and B multiplied by the angular speed along A, B. This gives us the velocity at the free end. Okay, now all keeping in mind that VA is equal to what? 0, since point A is fixed. So if V is 0, if you plug that into this equation, you're simply going to find the velocity at the free end, which is VB, to be equal to RAB multiplied by the angular speed AB. Now, since we're using vectors, always do well to indicate with this. So we need to find the position vector between A and B. That's what RAB means. Okay, now how do you find your position vectors? Let's take a look at the diagram once again. Position vector between A to B simply means moving from point A to locate point B. Now, we are not using the magnitude. In the previous question we solved, we used the magnitude between A to B, simply what? This radial arm. But using the vectors form now, I have to move from point A to locate point B. Remember the notation from the origin. If I am moving to my right horizontally, it is positive I. But if I'm moving backwards horizontally, it is negative I. If I'm moving vertically upward, it is positive J. But if I'm moving vertically downward, it is negative J. So I will move from point A now to locate point B. I will simply move from here to this point, covering this distance from here to this point, which is what? 6 inch. So to locate point B, first of all, I move from here to this point, covering 6 inch, and this is the I direction. So that simply means I have 6I, or 6 inch in the I direction, plus then I'll move from here to locate point B, covering this height, which is what? 12 inch. So to locate point B, my position is simply what? 6 inch plus 12 inch in the J direction. So that's 6 inch I plus 12 inch I. Okay. So RAB is equal to 6 inch in the I direction plus 12 inch in the J direction. So I'm going to now be using the converted values for 6 inch and 12 inch to represent these values. So this simply implies that RAB is equal to 6 inch. We obtain 6 inch to be equal to 0.1524 in meters. So that is simply 0.1524 in the I direction plus 12 inch, and we obtain 12 inch as 0.3048. So that is simply 0.3048 in the J direction. That is for 12 inch. So this is now our position vector between A and B. Now, having found this, we need to plug into this equation to obtain the velocity at point B, which is the velocity at the free end. Okay, so velocity at point B is equal to, we simply said, of course, V is 0, so that's off. So we have RAB, which is the whole of this, 0.1524 in the I direction plus 0.3048 in the J direction. So this cross the angular speed omega AB, and angular speed that was given to us is 10. And I said angular speed only moves in the K direction. So we simply have times 10 K. Okay, so this simply implies that VB is going to now be equal to, so I have K crossing everything in this bracket. So that becomes 10 times 0.152 being for the first one, 1524. Now the unit vectors, it is K crossing I. So I have K cross I. Okay, plus then I have 10 times, okay, 0.3048. Then I have K crossing J, so I have K cross J. So this simply implies that my velocity at point B is going to be equal to, now 10 times 0.1524, this will give me 1.524. Okay, now K cross I, not forgetting we said earlier K cross I simply gives us J. Okay, keeping this in mind, plus then we have 10 multiplied 0.3048. This will give us 3.048. Then I have K cross J, and K cross J, we said K cross J simply gives us negative I. Okay. K cross J simply gives us negative K cross J simply gives us negative I. So this simply implies that velocity at point B is equal to 1.524 in the J direction. Of course, this is minus 3.048 in the I direction. Keep this velocity component aside. So whenever you're analyzing kinetics of rigid body motion, always start from the fixed point. So we are done analyzing the fixed point A. We've obtained a value for velocity at point B. Next, we'll consider the fixed point D and obtain a velocity at point C. Okay, so remember, if point now, observe that if this arm AB is moving clockwise, that means BC will move anti-clockwise. Okay, if arm AB is moving clockwise, BC will move anti-clockwise, and if BC is moving anti-clockwise, it means CD is simply going to be moving where in the clockwise direction. So the angular speed here, omega CD, is in the clockwise direction as well. So if it is in the clockwise direction, remember at the free end we have a velocity which is at 90 degrees to the surface. That's simply called VC, the linear velocity at point C, and it must be in the same direction as what the angular speed. So now we need to find VC, okay, using the same equation, now relating the fixed points and what the radius D to C. So you now know that velocity at point C will simply be what? Velocity at point D, which is the fixed point, plus the radial arm between C to D multiplied by the angular speed C to D. Okay, but then VD is equal to 0 since point D is fixed. So it means this is simply 0. If that's the case, then velocity at point C becomes RCD multiplies omega CD, where omega CD is the angular speed along C to D, and of course RCD is the position vector between point C to D. So we need to find then what then is the position vector between point C to D. So if you look at the diagram once again, we want to find the position between C to D. Okay, so you observe that, like I explained here, if you're moving positively in the X direction, it is positive J, it is positive I, but if you're moving backward, that is negatively in the X direction, it becomes negative I. I want to find the position between C and D, which means I will move from here to this point. Now I am moving backwards horizontally. The distance itself is still 6 inch, okay, but I am now moving backwards. Which is now negative 6 inch. Then move from this height. Okay, so this is simply moving from here to this point. Okay, you're moving from here to this point, covering this distance 6 inch. Move from here to this point, covering this distance 6 inch. Then you move upwards in the positive J direction, which is 10 inch. So I am moving negatively, coming backwards. That's negative 6 inch. Then moving from here to this point, positive 10. So this is negative 6 in the I direction and plus 10 in the J direction. So position between C and D is simply what? Minus 6 inch in the I direction plus 10 inch in the J direction. So now we are going to be using the converted values of 6 inch and 10 inch into this equation. So this simply implies that the position between arm C to D is simply going to be equal to negative 6 inch, and 6 inch gave us 0.1524. So we have minus 0.1524 in the I direction plus 10 inch gave us 0.254 in the J direction. This is now our position. Now, keeping in mind that omega CD is always going to be in the K direction because the angular speed is always in the K direction. So having known this now, therefore, you can find the velocity at point C to be equal to, remember, position vector, which is minus 0.1524 in the I direction plus 0.254 in the J direction, crossing the angular speed, which is omega CD. Now this is going to be in the K direction. Okay, so this simply means that VC is equal to, I will simply have minus 0.1524 multiplied by omega CD. So omega CD. Now we have K crossing, this is I. Now, mind you, You can also do I cross K, right? Although there is going to be a difference in sign, but it doesn't really play much importance. But you can simply do I cross A, depending, of course, from this order, it's supposed to be like I cross A, okay? But I am doing it the other way around. So you can basically do this I cross K and, of course, J cross K. The signs might change a little bit, but you're still very much in order. Okay, so we have K cross I. Now this is plus 0.254 multiplying omega CD. So we'll have omega CD. Then we'll have K cross J. Okay, so we have K cross J. Now let's evaluate everything and see. So VC is simply going to be, now I, we have minus 0.1524 omega CD. K cross I simply gives us J, okay, plus this is 0.254 omega CD. Then we'll have K cross J. K cross J simply gives us negative I. So multiply negative I. So let's effect all of this. Alright, so upon evaluation, we simply have negative 0.1524 omega CD in the J direction minus 0.254 omega CD in the I direction. So keep this for velocity between velocity of point C. Now let's fall back to the diagram. So we've analyzed the two fixed points A and point D. Now we are left with motion between point B and point C. Now I said since this arm B to C is existing between 2 points or two fixed points A and D, then this is undergoing what is called the general plane motion, which is a motion that is rotating and translating at the same time. But since we're not using that particular method to solving this problem, rather we are making use of the vectors approach, you still maintain the same. So you can either pick point B or you can pick point C as your reference velocity and solve. But let's pick point C. Okay, so if you're picking point C, therefore VC, remember, is going to be equal to VB, velocity at the free end, plus you have RBC multiplied by omega speed BC. It's as simple as this, okay? Multiplied by omega RBC multiplied by omega BC. So if you're picking point C, it means you're moving relative to point B. So it becomes VC equals velocity at the free end VB plus, of course, radial arm multiplied by the angular speed. Or if you're picking point B, also it's still the same thing. VB is simply equal to what? It becomes velocity at the free end VC plus the radius arm multiplied by the angular speed along that arm BC. So it's basically what? The same thing. All right. We know what VB is. All we need to do now is find position vector between point B and point C. So let's take a look at the diagram once again. We want to find the position between B and C. Now we want to find the distance between point B and point C. So let's say, okay, we are moving from point C now. So remember, this height is given as 10 meters, whereas this height is given as 12 meters. So which means if we bisect, or let's draw a line, this is going to form a triangle. Let's just draw a horizontal line from here, from point C to point B, and you have something like this. So you see that this is automatically now a triangle having a height. And what is this height difference? That's what connects these points to point B. So if from here to this point is 12, and from here to this point, from the origin to point B is 12, and from the origin to point C is 10, that means this height alone is simply what? 2 inch. Keeping that in mind, it means this height is simply 2 inch. Now I am moving from point C. I want to locate point B. Remember, now I am going backwards, which means I am moving negatively in the x direction. And this distance was given here as what? 16 inch. So which means I am moving negatively in the x direction, which is minus 16 inch in the I direction. Then I'm moving vertically upwards, covering 2 inch. So plus 2 in the j direction. So therefore, the position RBC, okay, is going to simply be equal to minus 16 inch in the I direction plus 2 inch in the j direction. Okay, so let's plug in now their converted values. Mind you, We didn't convert 2 inch, but we can simply do that. 2 inch, okay, 2 inch is simply 2 times 0.0254. So we can get 2 inch in meters. So in meters, 2 inch is simply 0.0508 in meters. Therefore, the position between B and C is simply equal to negative 16 inch, and 16 inch gave us, remember, this is negative, okay, 0.4064 in meters. Okay, so simply, sorry, this is I, okay, plus 2 inch. 2 inch gave us 0.0508 J. So this is now the position vector between portion C and portion B. Okay, now if you know this, we can now plug into this equation. This simply implies that VC is equal to, we said VB, and we obtained VB earlier, not forgetting. Let's fall back to it. Not forgetting, we obtained VB earlier to be equal to this. So if this is VB, then let's plug it back into that equation. All right. So from the equation, VC is equal to VB, and these are the values of VB, and these are the values of VB plus RBC, and this is RBC obtained here, multiplied by omega BC, and of course omega BC is always in what, K direction. The angular speed is always in the K direction, so simply cross multiplying omega BC in the K direction. All right. So VC is now equal to, this is 1.524J, okay, minus 3.048 in the I direction. Now we are expanding this using the value to multiply omega BC in the K direction. So we are simply going to have minus 0.4064, okay, omega BC. Now we simply cross multiply the unit vectors. So remember, we maintain what we started with. So K cross, this is in the I direction, so K cross I, you have this. Okay, then we have plus 0.0508 in the J direction. Okay, multiply omega BC. So we cross their unit vectors. You have K cross the J direction, and you have this. So let's expand and see. So VC is equal to, you have 1.524 J minus 3.048 I. Okay, so let's now expand. K cross I simply gives us J. So that means we simply have minus 0.4064 omega BC. So let's collect like terms in unit vectors. Of course, we have VC to be equal to 1.524 in the J direction. Then I have over here 0.4064 in the J direction. So comparing the two of them together. Similarly, I have minus 3.048 in the I direction. Over here, I have minus 0.508 in the I direction. So comparing them together. Okay, so this simply means VC is equal to, we have 1.524 minus 0.4064 omega BC, all in the J direction. Okay, all in the J direction, plus over here we have, so we are simply comparing or factoring the unit vectors. Over here we have minus 3.048 minus in the I direction. Alright, so factoring out the unit vectors, we simply have this. So this is another equation we obtained for VC, but not forgetting that earlier we obtained an equation for VC. Let's just pull back to that side. Earlier we obtained this for VC. So since we obtain this for VC, it simply means this is going to be equal to the other VC which we just obtained now. So we are going to be equating the two of them together. Alright, so we obtain VC to be equal to this. But not forgetting earlier, we also obtained a value for VC to be equal to this. So which means the two of them are equal. We are then going to be equating the two of them together. Alright, so that simply means the whole of these values are equal to what? The whole of these values. So let's do it and see. So equating the two, we simply have this for VC equal to this, which is the whole of this equal to the whole of these values. Now what we'll do at this point is comparing like terms in unit vectors. So we are simply going to be comparing the unit vectors. So those in the I direction over this side of the equation will be equal to those in the I direction on this side, and those in the J direction on this side of the equation will be equal to every term on the J direction. So we are simply comparing like terms in unit vectors. So I have here minus 0.1524 omega CD in the J direction. So this is going to be equal to all these terms in the J direction. Similarly, I have here 0.254 omega CD in the I direction. So since this is in the I direction, it's going to be equal to all these terms over here in the I direction. So we are going to have two different equations. Let's form them and see. So by so doing, we have two different equations, equation 1 and equation 2, which arises from the comparison of unit vectors. Now, let's pull back the diagram and see. So once more, this is our diagram. We were asked to find the velocity of the rack VR, okay, which is causing motion of this arm CD. So you know that this rack is responsible for the motion of this arm CD. So which means if the rack is moving, the gear is moving, and of course the arm D to C is also exhibiting what? Rotation. So that simply means that the velocity of the rack is equal to the velocity of this arm CD, and the only velocity recognized in this arm, remember VD is 0 because this point is fixed. So the only velocity recognized in this arm is velocity at point C, which is VC. So that simply means if we're able to find VC, VC can be equal to what? Velocity of the rack, VR. Now, keeping that in mind, that simply means we need to find the angular speed along this arm D to C. So we need to find omega CD or DC. If we can get the angular speed along this arm, then we can find the velocity at point C. And if we know the velocity at point C, then we know the velocity of the rack. Okay, so that simply means in this equation, all we need to do is find what? Angular speed along CD, which is omega CD. So that means we can pick any of the equation and solve in terms of DC, either use and solve in terms of BC, making BC subject to the formula and then putting it in the other equation so that everything becomes in terms of DC. Then we can find the angular speed along DC or along CD. Okay, so we can simply start from equation 1, make omega BC subject of the formula. So from 1, okay, we simply make omega base is subject of the formula. Therefore, we send this term over to this side of the equation. Remember here we have minus 0.1524 omega CD. Now, if this cross an equal to sign, it becomes minus 1.524. And this is going to be equal to, I have left here, minus 0.4064 omega BC. So we simply make omega basis subject of the formula and impute that into equation 2 and find the value of the angular speed along CD. Okay, so therefore omega BC is going to be equal to, so to make omega BC subject, we divide all through by the coefficient of omega BC, which is minus 0.4064. So we have minus 0.1524 omega CD all over minus 0.4064 minus 1.524 all over minus 0.4064. So, okay. So this will give us a value for the angular speed along BC. All right. So let's divide all two and obtain a value. So upon division, we have our angular speed along BC to be equal to this. Mind you, negative sign cancels negative sign. Same thing here, negative sign cancels negative sign. So everything becomes positive. Now we can call this equation 3. So we simply plug equation 3 into equation 2 to find the angular speed CD. So from 3, okay, we had minus 0.2, we have minus 0.254 omega CD to be equal to, so this is our equation 2. We simply plug this into this equation in place of omega BC. Therefore, we have minus 0.254 omega CD to be equal to minus 3.048 minus 0.0508 into, in place of omega BC, we'll put in these values. We have 0.375 omega CD plus 3.75. All right, so let's now expand this bracket. We have minus 0.254 omega CD to be equal to minus 3.048. Let's now use minus 0.0508 to expand the whole of this bracket. All right. So upon expansion, we simply have this. Now we'll collect like terms, bring angular speed CD together. So I have minus 0.254 omega CD. Now I'll simply bring minus 0.01905 omega CD over here. So I have plus, it becomes positive now, 0.01905 omega CD. And this is equal to, over here I have minus 3.048. I have here minus 0.1905. Okay, so let's evaluate these values together. So minus 0.254 omega CD plus 0.01905 gives us approximately minus 0.2350 minus 0.2350, okay, omega CD, and this is equal to, over here we have minus, so over here we have minus 3.2385, 2385. Therefore, in order to obtain the angular speed, we divide both sides by the coefficient of the angular speed. So this simply implies that omega CD is equal to minus 3.2385 divided by minus 0.2350. So this simply implies omega CD is equal to, that gives us approximately 13.78 in radian per second. So this is the angular speed of CD. So you recall that velocity of portion C is definitely going to be the position of portion C, okay, relative to D multiplied by angular speed of C relative to D. So since we know the angular speed now, we need to now find the position between C. Already we found the position, but now when solving this problem, we are not going to be using the position in vector form. We are simply going to employ the magnitude of this position to multiply with this so that we can obtain an actual value. All right. Okay, so we already know the position between CD. So arrow CD is already known, and we know omega CD. Remember, omega CD is always in the k direction. So we can obtain their vector multiplication, or you can simply use the magnitude to multiply with this result and also obtain the magnitude of that speed. But since we're using vector form, it means our result will also be in vector form. Okay. So once again, let's take a look at the diagram. The position between point B The position vector between point D and point C, I explained this earlier, and we obtained, of course, moving from D to C, you have to move backwards covering 6 inch, and then you have to move up covering 10 inch. So we have 6 inch or negative 6 inch in the I direction and plus 10 inch in the J direction. And of course, we had this to be equal to this. When converted to meters, we had our negative 6 inch to give us minus 0.1524 in the I direction plus our 10 inch to give us 0.254 in the J direction. So this is now the position vector in vector form, and this is our angular speed. Remember, I said angular speed along CD, of course, we obtain 13.78, and I said it is always in the K direction. This simply implies, therefore, that the speed of arm C is going to be equal to, in vector form now, will be the position vector between arm CD multiplied by the angular speed along arm CD, being a cross product. So this simply means velocity at point C is equal to, now we have minus 0.1524 in the I direction plus 0.254 in the J direction. This is cross multiplying 13.78 in the K direction. So this simply means VC is going to be equal to, remember, we have minus 0.1524 multiplying 13.78, then we'll have K crossing I. So we maintain K cross I all throughout the calculation, but I also said you can do I cross K and J cross K. The only thing that will change is the sign, but it doesn't really mean you're wrong. Okay. So now with point minus 0.1524 multiplies 13.78, and we are going to have, so minus 0.1524 multiplies 13.78. This gives us approximately minus 2.1. Then we'll have K cross I, and K cross I simply gives us J, plus now we do 0.254 multiplies 13.78. That gives us approximately 3.5. Okay, then we'll do K cross J, and K cross J simply gives us minus I. Mind you, like I said, you can also do J cross K, but we maintain K crossing all of them from beginning, so we have to maintain that energy all through. So this simply implies that velocity at point C is simply minus 2.1 J, and this is minus 3.5 I. All right, so velocity of the rack, as I explained earlier, V arrow is equal to VC. So the rack will moving at the same speed as the velocity at point C, and this is equal to minus 2.1 J minus 3.5 I. So this is the unit vector of the velocity of the rack, or the velocity of the rack in vectors form. But you can also find the magnitude. To find the magnitude of that speed, V arrow magnitude is going to simply be the square root of minus 2.1 all squared plus minus 3.5 all squared. So if you do this, you're going to obtain a value which can also be termed as the magnitude. So let's do it and see. So in terms of magnitude, we have velocity of the rack to be 4.08 meters per second. So that is the velocity of the rack. All right, guys. So that's it on that question, and that is how to employ vector form to solve kinetics of rigid body. You can also use the other ones I've solved previously, which is not a vector form, and you will still obtain the same result as we've obtained here. All right, guys. I will see you in the next video with another question on kinetics of rigid body. Thanks and cheers.